the electric dipole and the electric field due to a dipole first on its axis and then on an equatorial line. So let's deal with the electric field due to a dipole at its axis. So we'll be checking out what is the electric field due to a dipole on its axis. Suppose I have a dipole over here. What is a dipole? Equal and opposite charge separated by a small distance. Suppose this is the center of the dipole and I take this as L and this also as L. So the total length of dipole becomes 2L, and I need to find the electric field on the axis of dipole. This is the axis along this line at a distance r from the center of the dipole. I have taken the distance from the center of dipole at some point over here. Now what is the net electric field due to both these charges? The electric field due to this charge, I am calling it 1 and calling it 2. Due to this charge plus Q at this point will be away from the charge because it is a positive charge. So this is E1, electric field due to the point charge Q at this point. And electric field due to the minus Q charge will be towards this charge like this, E2, because this is a negative charge and electric field due to a negative charge is towards the charge. So what will be the net electric field? Yes, you know it. It will be somewhere E1 minus E2 if E1 is bigger than E2. Or anyways, it is the vector sum and both are in opposite direction. So what is E1 and E2? We need to calculate, of course. So E1 is the electric field due to the point charge plus Q. It will be 1 by 4 pi epsilon naught multiplied by Q upon the distance of this charge from the point. Now this whole is R, this is L. So the distance of the charge from the point will become R minus L. So it will be R minus L whole square. The distance of this charge from this point is R minus L. This is R and this is L. What is E2? E2 is the electric field with the charge minus Q. So let us calculate E2. It will be 1 by 4 pi epsilon naught multiplied by charge upon its distance. Now how far is this charge from this point? Yes, it's R plus L. This is R and this is L. So R plus L. R plus L whole square. So these are the two electric field with the point charges. Now you can see E1 is greater because this term is smaller and this is larger. So I'll put it over here, 1 by 4 pi epsilon naught Q upon R minus L whole square minus 1 by 4 pi epsilon naught Q upon R plus L whole square. Let's subtract it. I'll take 1 by 4 pi epsilon naught common, Q common, so I'll get 1 upon R minus L whole square minus 1 upon R plus L whole square. Solve this, take LCM and solve this. On solving, you'll get it as 1 by 4 pi epsilon naught multiplied by Q multiplied by 4RL upon R square minus L square whole square. You'll get this. Now I have to rearrange terms. How? Look, I'll do it like this. 1 by 4 pi epsilon naught multiplied by Q multiplied by 2L multiplied by 2R. You must be confused why I'm doing such things. Okay, I'll explain. There is a term called dipole moment P, which is Q multiplied by 2L. If you haven't watched my previous lecture, go and watch and learn what is a dipole moment. It is Q, the charge, multiplied by the distance between the charge. So Q into 2L will become P, the dipole moment, 1 by 4 pi epsilon naught multiplied by P multiplied by 2R. So I'm writing 2PR divided by R square minus L square whole square. This is the electric field at the axis of dipole. This is not 12, this is not 12, this is just 2PR. This becomes P and this is 2R, 2PR upon 4 pi epsilon naught R square minus L square, whole square. This is the electric field at this point P. So it will become E is equal to 1 by 4 pi epsilon naught multiplied by 2PR upon R square minus L square whole square. So this is the electric field at the axis of dipole at a distance r from the center of dipole. Now there is an extension to this formula and that is really important. What is that? First you note down this and please learn it. Okay, so what's the extension I'm talking about? In our common day life, the dipole is very small. It's very small. Yes, the length of the dipole is very small. So this length is very small compared to the distance r. So in front of r, L will nearly tend to 0. So the electric field at the axis will change to 1 by 4 pi epsilon naught multiplied by 2 pi r upon r squared ka whole square, because that L will get cancelled. This will be r to power 4, and when you will check it, so you will get r get cancelled, so you get r cubed. So this is the electric field at the axis of dipole. Is the expression complete? Is it full? No, it's not full, it's not final. Why? Because electric field is a vector quantity and we have not identified what its direction is. So we have to check what its direction is. Definitely E1 was greater than E2, so this is the direction of E at the axis. Yes, it's like this. How can you give this direction? Away from positive charge, away from negative charge? No. Listen, this is the direction of dipole moment. It's always from negative charge to positive charge, the direction of dipole moment. You can see the direction of dipole moment and direction of electric field is same. So you can put a vector sign and complete. So this is the expression. Learn it, check it, and derive it.